All right, so we know that they're perpendicular if their dot product is 0, and so we're going to write the dot product out, negative 4t plus t plus 2 times 1 plus t, and then plus negative 3t or minus 3t. So remember, the dot product is when you multiply the first one times the first one, and then you add that to the second times the second, and then add that to the third times the third. And if they're perpendicular, the dot product would be 0. So we're going to just simplify until we have a nice quadratic equation. So I can combine those two to make negative 7t. And I get t minus t squared plus 2 plus 2t. So I combined these two to make negative 7t, and then I multiplied those out. You don't have to do exactly in that order, but you should end up with the same thing as me. Oh, sorry, it says minus. Why does it say minus? It should be plus, right? Yeah. All right, so I've got t squared first, and then negative 7t, 1t, and 2t, so negative 4t, plus 2 equals 0. Yeah. I try to make my t's have like a curved bottom so they don't look like a plus, but my pluses aren't that straight either, so it's hard to tell. But it is t squared minus 4t plus 2 equals 0. How do we solve this quadratic equation? Plug it in where? So we could graph it in the calculator, yeah. We could use the quadratic formula. Anything else? We could see if it's factorable. Did anybody try to see if it's factorable? Unfortunately, no, because we would need two numbers that multiply to 2 and add to negative 4. I love factoring, but this is not a factoring problem. So yeah, pick your favorite method, quadratic formula, or you can graph it on the calculator. We should get the same answer, and that's always fun to...
Do you have to simplify, or can you just use 2 plus or minus?
Yeah, you would have to simplify in these cases to get your 3 sig fig answers. Yeah. So some people use quadratic formula, and some people use the calculator and the second trace 0 feature for that. Okay. All right, so that was review. We're moving on to our new notes. We're going to write the vector equation of lines today. Vector equation of lines. All right, there's a lot of conversations going on right now, which makes it a little hard for me to start in here. All right, in both 2-dimensional and 3-dimensional geometry, we can determine the equation of a line. The equation of a line using its directions and any fixed point. Directions and any fixed point. Okay? So, I mean, think about that. That's kind of what we do in like slope-intercept form. When we write y equals mx plus b back in Algebra 1, b was a point. It was your y-intercept. And then m was your directions, because your slope is just saying how much do you go up, how much do you go over. It's the same thing with vectors. It just looks different. And it's saying you can use any point. Like, there's nothing magical about the y-intercept. You don't have to start there. You can start at any point on the line and then use that slope to graph your line. In 2 dimensions, we are dealing with a line in a plane. So in 2 dimensions, your line sits on a plane. And in 3 dimensions, we're dealing with a line in space. All right, suppose a line passes through a fixed point A with a position vector A, and the line is parallel to vector B. Consider a point on line R on the line with position vector R. By vector addition, R is equal to A plus AR. So here's AR. So R is equal to A plus AR. That's kind of what we did at the beginning of class when we added two vectors, right? So this vector plus this vector is equal to this vector. And since AR is parallel to B, what is this Greek letter? Is that a lambda?
That's L.
Is it lambda though? Is that how you say it?
Oh, okay.
You guys don't know? Let's look it up. I don't know either. I'm going to say, what does lambda look like? We'll see if we get it. All right. But here's the deal, guys. R is equal to A plus lambda B is the vector equation of the line. Okay, and we're going to turn the page because it says suppose R, which is x, y, and z, is any point on the line. Okay, and A1, A2, A3 is a known or fixed point on the line. Oh, sorry. And B is going to be the direction vector of the line. This is how we would write the equation. So we would say that the point XYZ is equal to the starting point that we just picked. It could be any point on the line that we picked. Not any point in space, but any point in the line that we picked. Plus lambda times your direction vector. This is the vector equation. It looks new, and yet it's not really new. All right, and then the parametric equations of the lines are these. So parametric equations, instead of having x and y and z in the same equation, it is a set of equations where x and y and z are all determined in terms of lambda, which is the parameter. So lambda is in the set of real numbers, and lambda is the parameter. Okay. It makes much more sense in context, so we're going to do an example. A line in space passes through this point, 1, negative 2, 3, and in the direction 4i plus 5j minus 6k. Do you know why we use these unit vectors so much? Because it's like really hard to draw a column vector on a document, so we use the unit vectors a lot. All right, describe the line using a vector equation. So x, y, and z are going to be the variables, x, y, and z. And it's going to equal your starting point, 1, negative 2, 3, plus lambda. Remember I told you lambda just comes up a lot because it's our parameter, times your direction vector. So even though the direction vector is written in unit vector form, we need to write it in column form. 4, 5, negative 6, okay? All right, guys. How simple was that? We just wrote a vector equation. You got your starting point, and then lambda times your direction vector. There's nothing to solve because it's an equation. It's an equation in 3 variables. You can write this as a set of parametric equations too. Look at the parametric equations. It's just taking apart the vector equation. So if this is my vector equation, the first line is my x, the second line is my y, the third line is my z. So x equals 1 plus, I'm going to write 4 lambda because that's just the way we use variables. Y equals negative 2 plus 5 lambda. And z equals 3 minus 6 lambda. There's nothing to solve. They're equations. So I said write an equation. Remember, an equation has many points that would make solutions for it. Okay. All right, 2 says find parametric equations for the lines through these 2 points. So what we need to do is we need to find the vector through those points. So we're going to find vector AB. All right, so to find vector AB, we're going to do B minus A. So vector AB, negative 1 minus 2. 0 minus negative 1, which is plus 1, and 2 minus 4. So we're going to get the vector first, and then we'll write the parametric equations from it. So I'm getting negative 3, 1, and negative 2. All right. Does the vector describe the starting point or the direction? Yeah, the vector describes the direction. So we still need a starting point. And you can use any point on the line for your starting point. So which point could we choose? We could choose point A, right? Or we could choose point B. You get to pick. All right, so you get to pick which point you want for your starting point. So the equation, I'm going to write it out first before parametric form, all right? The equation would be xyz equals, choose a point. It was suggested to choose A, but you could just as well choose B. 2, negative 1, 4, plus lambda. And then we need to use the direction vector. Okay, a point plus lambda times the direction vector. So it can be difficult to wrap your head around what lambda would be, because it's kind of like another variable in there, right? And it's the parameter. Most commonly, the parameter is time. So as time passes, your x, your y, and your z change, and in a predictable way. So like after 2 seconds, the x and the y and the z have changed by twice this direction vector. Now it doesn't say the parameter's time here, and it doesn't have to be time, but that's the most common parameter that you use in parametric equations. Yes?
Did we not use the other equation?
The other point, B?
No, like, it says parametric.
Oh yeah, we haven't written those yet, right? So we still have to do that. So yes, we haven't finished the problem. So x equals 2, I put plus. You could put minus though. I have plus negative 3 lambda. Y is equal to negative 1 plus 1 lambda, or just plus lambda. And z is equal to 4 minus 2 lambda. All right. So that's your final equation, because it said to write them as parametric equations. Could you just go straight to this answer? Possibly. You could definitely skip this middle step. That was just kind of to show you where everything came together. You probably would need to show AB, especially like on your test, right? Any questions before we move on? You might notice the next section is really just reviewing the equation for the angle between two vectors. That's not new. You've seen that equation before, right? Cosine of theta is equal to the magnitude of the dot product over... actually, that would be the absolute value of the dot product over the magnitude of b times the magnitude of b2. So dot product gives you a number answer, right?
Yes.
When you have a number answer, you don't want to talk about magnitude because it's already a number. These bars mean absolute value. But that down here, B1 and B2, those are vectors. For those, we're doing magnitude. So the bars have two different meanings here. Okay? So if you have bars on, sorry, you can't even see that. If you have bars on a dot product, that's absolute value. And then if you have bars on a vector, that's magnitude. Okay, let's turn the page. All right. So we have parametric equations here. And what we need from these parametric equations are the vectors. The vectors come from the direction part of the equation. So those would be the parts on the variable. So you might be able to pull out your direction vectors right away. I'm just going to write them as vector equations. So I have xy is equal to 2, -1, 2, -1, plus t, -3, 1. Okay, so I wrote that as a vector equation because what I want to do is pull out this direction vector. That's the part that I need to find that angle. Go ahead and write L2 as a vector equation. Yes, Evelyn. All right, so for L2, you should have xy equals 1 -4 plus s times 2, 3. And these are your direction vectors. This is the important part. This one and this one, those are the direction vectors. So when we do the cosine formula, you're going to be using those two vectors to do your dot product and your magnitudes. So the formula is cosine theta is equal to the absolute value of the dot product of L1 and L2 over the magnitude of L1 times the magnitude of L2. That formula is the same formula, it's just the variables look different. That's the cosine of the angle. Well, it comes back from when we defined these in the first place, but it's the one that has the variable on it, the parameter on it. L1, L2. Yeah, L1, L2. So I'm going to do dot product on the top. So cosine theta is going to be the absolute value of -3 times 2 plus 1 times 3. And then in the denominator, the magnitude of L1 is -3 squared plus 1 squared. And then the magnitude of L2 is 2 squared, square root of 2 squared plus 3 squared. We've done this formula before. All right, so I get -6 plus 3 is -3, and then the absolute value makes it 3. And then square root of 10 times the square root of 13 gives me the square root of 130. So on the top, I just multiplied and added and took the absolute value. On the bottom, I got the square root of 10 times the square root of 13, which is the square root of 130. And now that's what cosine theta equals. So to find theta, I need to do inverse cosine. So I'm going to do theta is equal to inverse cosine 3 over square root of 130. Okay, so I'm going to give you a minute to catch up and to find that final answer. Bruce. All right, so 74.7 degrees is the angle between the two vectors. So notice you just needed their directions. That's it. Okay, reviewing parallel and perpendicular lines. Two lines are parallel. Two vectors are parallel, sorry. Two vectors are parallel if one of them is some constant times the other one. It says scalar k, so it has to be a constant number. And then they're perpendicular if their dot product is 0. So I'm going to use this definition to show you that these two lines are, sorry, it says find the angle between the lines. Okay, so actually I'm not. I'm gonna do the same thing. We can do the same thing here to find that the angle between these two. But what do you notice about their direction vectors? What's that?
A different letter.
Oh, they have different letters. Yes, very nice. But what do you notice about the numbers in these vectors?
There's 3 of them.
What's half? Who said that? Okay, Sally, tell me more. What's half of what? What's that? They're half of each other? Okay. And then Sophia adds in negative half of each other, right? So we could say that the first one is negative 0.5 times the second one, right? So if the lines are parallel, remember that for vectors, because vectors can be put anywhere, if they're parallel, they're actually on the same line. What would be the angle between them if they're on the same line? Not 90. They could be this way or this way or this way. I'm not asking about their slope. What's the angle between the two lines if they are the same line? 0. 0. There's the angle between the two lines is 0 if they're actually the same line, right? If they were a little bit apart, maybe it'd be like 1 degree or 2 degrees, but if they're the same line, the angle between them is 0. I'm not asking for the slope of the line. I'm asking for the angle between the two lines, or the vectors, sorry. They're vectors, okay? So, if you notice that, then you could avoid doing all of this to get 0. And you could say, since they are parallel, they're parallel, and you can show that method, the angle is 0. I don't think we need to practice the exact same thing we did, so we're going to do that second method. But know that if you did do all those steps and you got that the angle is 0, that's good too. That's fine. All right? But here's what we did. We noticed that -3, 1, -2 is equal to sum k times 6, -2, 4. 3 is equal to, no, -3 is equal to k times 6, and we get k is equal to -1/2. And it works for all of them. 1 is equal to k times -2. K is equal to -1/2. -2 is equal to k times 4. And k is -1/2. So therefore, the vectors are parallel. And the angle is 0 degrees. So you could do the exact same method as before, or you could notice that and save yourself a little bit of time. Say it again. I can't hear you over all these papers. Give me a sec. Constant velocity. An object moving with constant velocity will travel in a straight line, and to model using vectors, the velocity vector of the motion will give the direction of the line. Ooh. Velocity vector of the motion gives the direction of the line, and time will be the parameter. Okay? So time is the most common parameter. The initial position of the object gives a fixed point on the line. So remember, your vector equations have a point on the line, and then they have a direction vector, which in this case would be the velocity vector. Let's see. So here is the equation. If an object has initial vector A and moves with constant velocity B, then its position at time t is given by r is equal to a plus 2b, and notice r is this vector here. The speed of the object is the magnitude of the velocity vector. Magnitude. Yeah, but they're saying that velocity could be negative, but not speed. Okay, so the speed of the object is the absolute value of b, which is the magnitude of the velocity vector. Okay, look at number 5. You see two vectors there. Which of the vectors shows the initial position of the object? 1, 9. I heard a vote for 1, 9. Is 1, 9 the one that shows the initial position?
Yes.
Hi. Be right back. So, just like you predicted, the initial position was 1, 9. When I write it as a point, I write it sideways with a comma. So, when you're trying to write a point, this way, okay? Plot the path of the object for t equals 0, 1, 2, and 3. All we need to do is substitute these numbers for t. So, for example, 1 plus 0 times 3, 9 plus 0 times negative 4. Okay, so for t equals 0, you just substitute 0 for the time, and you find the point. So I got the point, let's see, 1, 9. Let's see. All right, the next one, when you substitute 1, it's going to be 1 plus 1 times 3, 9 plus 1 times negative 4. So I get 4, 5. Is that right, Nate? Yeah, 4, 5. It's right here. I feel like I'm off a little bit. Is that 4, 5? Yeah. All right, do you see what we're doing? We're substituting 0 for time, then 1 for time, and then we're going to do 2 and 3. And what you're going to notice is that these points are going to land on a line with a constant slope. The slope comes from your direction vector. All right, 1 plus 2 times 3, 9 plus 2 times negative 4. So that's 6, 7, and 1, I think. 7, 1. Okay. What's the slope of this line? What's the gradient of this line? Negative 4 is your rise, right? And 3 is your run. So negative 4 over 3, that's the change in y over the change in x. You see how it comes from your vector? It's just written backwards from a slope because this is written x first and then y. When we write slope, we write change in y over change in x. So this can also tell you the slope of your line. And I think we need one more point. Is it at 10, negative 3? Yeah. Okay. And I didn't substitute that one in, but I think you guys saw what we were doing. All right, so this is really how parametric equations work. As time passes, the x and the y and sometimes the z change. And so you can find them and they land on a straight line. Find the velocity vector of the object. Well, if this is the initial position, then that means this one is the velocity vector. So it's just 3, negative 4. And to find the speed, we just need to find the magnitude. So find the magnitude of that vector. Share your answer with a neighbor. All right, square root of 25 gives us 5. Good. So it's 5, and I think we have a unit. Meters and then per second, because it's a speed, right? Meters per second. All right, the object continues to move in the same direction, but increases its speed to 30 meters per second. Do you notice how the IB writes meters per second? I don't love it, but that's what they do, so you need to get used to seeing it. This meters per second means the same as this meters per second. All right, so just notice those two notations. They are the same thing. State the new velocity vector. So our new velocity is k times our old velocity. So it would be 6 times our old velocity. So what we're going to do is just multiply your velocity vector by 6. So this is our velocity vector. All right, turning the page. A mermaid is initially at 15.8 negative 1. Why is the z direction negative? She's under the water. Yep. Okay, so she's got coordinates 15, 8, and then her depth is negative 1. Find the position of the mermaid after t seconds. What that means is write an equation in terms of t, okay? So write the vector equation using t as your parameter. I'm going to let you guys do the rest of it yourself. I just didn't think that that was clear. All right, and I want you to try A, B, and C. I'll come around and see if you need any help. Okay, so let's check what you've done so far. So first you're writing the equation with t as your parameter. So you started with xyz equals, and then this is your initial position plus t times your velocity vector. And that's it. That's just the equation. For the next one, to find the speed of the mermaid, we need to use the velocity vector and find its magnitude. And I'm going to get square root of 54.25. Which to 3 sig figs would be 7.37. Oh, let's practice writing our unit the IB way. Meters per second. All right, when the mermaid reaches the depth of 28 meters, the z value equals what number? Negative 28, because it's below the c, right? So z is negative 28. And we're just going to use the z part of the equation. So negative 28 equals negative 1 plus t times negative 9/2.
Did you substitute negative 9/2 for negative 4.5?
Yeah, so Caden likes negative 4.5. I do too. I'm going to start by adding 1 on both sides. So negative 27 equals negative 4.5t. And then you're going to divide by negative 4.5. You can divide by negative 9/2 too. It's just a little bit extra typing. And did you guys get 6 seconds? Okay. Are you talking to me?
Yeah.
Louder. superior you over them. Do you get points taken off, Sally? What'd she say? You get points taken off of what, Sally? Oh, it's positive. Well, you'll get a different answer, right? You understand that? If you write 28 as positive, you'll get a different answer. I get that it's a little bit tricky. I completely understand that. And so you just have to kind of read it in the context of the problem. Okay. All right, we're going to continue on. So we're going to talk about intersecting lines. So in two dimensions, we call these intersecting, we call these parallel. And these are like two lines that are actually the same line. We call them coincident. So it says vector equations of two dimensions can be solved simultaneously to find the point where the lines meet, and that's like a system of equations. So what we do is we write an equation, we write two equations about S and, wait, I'm not saying that right. Oh, we want to know where they meet. So we write an equation about the x's being the same and an equation about the y's being the same. So for the x's, I could say negative 2 plus 3s, right? Negative 2 plus 3s. And I want to know when it has the same x as the other equation, so that would be 15 minus 4t. So I want to know when the x's are going to be the same, and then I also want to know when the y's are going to be the same. So the y's are going to be the same when 1 plus 2s equals 5 plus 1t. All right, so we have solved system of equations before, and there are a few different methods on your calculator to do it. Some of you have found the Pauli function in your calculator. Mabel, I know that Ms. Young likes that one a lot, right? Yeah, and so you can use that. Some of us had trouble getting it onto our calculators, so we went to different methods. There are different methods. There's a matrix method, and then there's simply a graphing method. And graphing is the one I seem to use the most. But if you have a different method you want to use, you can do that. In order to graph, I need to solve for one variable because my calculator has y equals in it. You don't have to solve by graphing. You can use any of those other methods. You can even solve this without a calculator. This is an Algebra 2 problem, Algebra 1 problem. You can solve this without a calculator, but it might not be the quickest way. So to solve it by graphing, I need to get a variable by itself, and I just chose to solve for s because it's already on the left side, but you can solve for t, it doesn't matter. So I'm solving for s. So I get 3s is equal to 17 minus 4t. And then dividing it by 3, I have s is equal to 17 minus 4t over 3. I don't have to actually distribute or anything like that, but I do need the parentheses. And on this one, I'm going to solve for s as well. So I have 2s equals 4 plus t. And dividing by 2, s is equal to 4 plus t over 2. And then I'm going to graph this in my calculator. Again, if you're using a different method, totally fine. We should get the same answer. So I'm going to freeze this for a moment while I put this into the calculator. All right, so to solve it by graphing, you put those in, you graph it, and you can kind of eyeball where the answer is, but just to be sure you have it right, you do second, trace. I want to know where the lines intersect, that's 5, and you press enter 3 times. 1, 2, 3. Okay, so they're crossing at 2, 3, but I need to interpret that answer now. They were crossing at 2, 3. All right, so 3 is my y, so that was my s. And then 2 is my t, so that goes here. And so now I can use these to find the x and y where they meet. You can put these s and t into either of the equations to find x and y, either one. But if you really want to make sure that you did it right, you can put it into both equations and make sure that they match up. So I'm going to put them into both equations. Technically, just putting into one should be fine as long as you know you're right. All right, so x, y equals -2, 1 plus s, which is 3, times 3, 2. All right, so that would be 9 minus 2, which is 7. And then 1 plus 6 is also 7. So I'm getting 7, 7. And so 7, 7 should be the point where the two lines meet. But I can do the other equation just to make sure I did it right. So the other equation is xy equals 15, 5 plus t is 2 times -4, 1. All right, and I also get 7, 7, so I know now that I've done it right. So I can say, therefore, the lines cross at 7, 7, written as a point this time. Okay, boat A moves according to this equation, and t has to be greater than or equal to 0 seconds. And then boat B moves according to this equation, also t is greater than or equal to 0 seconds. So we're trying to find the point where the paths of the boat intersect. And so we're going to write the equation about the x-coordinates being the same. So the first time we're going to call time 1, t1, and the second one we're going to call it t2. And so for the first equation, I have -1 plus 2 times t1. And then the second equation, I have 15 minus 1 times t2. And then we're going to do the y's. So for the y's, I have -5 plus 3 t1 is equal to, and then over here, -16 plus 2 t2. So we have the two equations. And then for each equation, I solved for the time 1. So I isolated time 1 so that I could solve it by graphing. Now remember, there are lots of other ways you can solve on your calculator, but I chose to solve by graphing. And when I got the point of the intersection, then it was 10, 3. I had to go back and say, okay, I put t1 for my y, so that means 3 is my y. 3 is my t1, and then 10 is my t2. So then putting that back into either equation, so I would take my first equation and I could put 3 for the t1 and I would get 5, 4. And that tells me that their paths cross at 5, 4. But just to be sure that I did it right, I can use the second equation and put 10 for t2. And I also get 5, 4. So now I'm sure I did it right. To find out, will the boats actually collide at this point, we want to know if they cross at the same time. But they don't. They're different times, so they will not actually collide. All right, and we do Q the same way. Even though there's 3 equations, we're only going to try to see if 2 of them at the same time intersect. So we're looking to see if lines 1 and 2 intersect. And so we set the x's equal, we set the y's equal, and we set the z's equal in lines 1 and line 2. And so we get 3 equations, and I isolated s in each equation. So these are my first 3 equations, then I isolated s in each equation and I graphed them, and all 3 crossed at the point 1, -2. And so because I isolated the s, that makes the s my y. So s is -2 and t is 1. I can put -2 back in for s, and I can get that this is the point where the two lines intersect at. For lines 2 and 3, I did the same thing, but when I graphed the 3 lines, and this time I isolated t, they didn't cross at the same point. So that means that there's no solution. There's no common intersection.